We've seen that magnetic fields can be created by magnets, but they can also be created by electricity. Electromagnetism describes all the phenomena resulting from the interaction between electricity and magnetism. To generate a magnetic field using electricity, the electrical charges must be in motion. In other words, there must be electricity flowing in a wire. If there's none, then there can be no magnetic field. And the magnetic field will last only as long as the current flows. And this phenomenon allows us to use many devices such as electric motors, speakers, doorbells, or electric generators. So far we've seen the shape of a magnetic field around bar magnets and horseshoe magnets. But if we use electromagnetism to create a magnetic field around a live wire, which is simply a straight wire, like drawn down here, well, the magnetic field will have a different shape. So if an electric current passes through a live wire like that one, the magnetic field will form circles around that wire. You could imagine an infinite number of those circles, and if we looked at the wire right in front of it, each circle would form a right angle with that wire. So the magnetic field is always perpendicular to your wire or to your current. It's one thing to know that the shape of the field is a circle, but you need to be able to predict its correct orientation. And to do that, we're going to use a trick called the right-hand rule. When using that trick, make sure you use your right hand. And then start with your thumb, pointing in the current's direction, which is always from positive going towards negative. So your thumb should be pointing to the left side right now. And your 4 other fingers, you're going to imagine that you're grasping the red wire as if you were grasping a pole or a real wire. And the fingers should be rolling around that wire, following the arrows that I've drawn on that wire. So it's showing us that the field is going up in front of the wire, and then it goes back behind the wire. Now for the second wire, the current was reversed, positive going to negative. So you turn your right hand around, your thumb now points to the right side, and your fingers wrap around that wire. And it shows you that when the fingers go up, they're moving behind the wire, and as they come back down, they're moving in front of the wire. So the current always flows from positive to negative, and the magnetic field is always perpendicular to the current, never in the same direction. You can use this slide to practice your right-hand rule, and you can use the 2 vertical wires and try to find where the positive and negative ends of those wires are. The next section is for high science only, the magnetic field of a solenoid. A solenoid is a conducting wire that you simply loop around many times to form a coil, like this. And by applying an electric current to the solenoid, a magnetic field is also created. And since that wire is coiled around, the magnetic fields will be added together and end up forming the same shape as we had on a bar magnet. So when finding out the magnetic field of a solenoid, we're going to have to look carefully at the positive and negative terminals of our system. We're going to have to use a north and a south pole, because since the field is like a bar magnet, we will create a north and a south magnetic pole. And we'll have to be careful looking at where the wire passes. So here the wire passes in front, and here the wire passes behind. So we'll have to watch out for all those things. To be able to predict the correct orientation of the magnetic field in a solenoid, we need to use another trick. This one is the second right-hand rule. This trick begins with the 4 fingers this time, so it's different from the first one. You always have to find where the current is going. So the 4 fingers, they travel from the positive to the negative. So imagine that you follow this blue wire here with your 4 fingers. So the current is going up. So your fingers start by going up, and then you wrap them around the hollow tube in the center. So your fingers loop around just like the blue wire is doing. And once you've wrapped your fingers around, you point with your thumb. If you did this properly, your thumb should be pointing left, meaning that the left side of that magnetic field is the north magnetic pole. The right side will there be the south magnetic pole. and the resulting magnetic field would look like this, just like the one around the bar magnet. We can add a few lines like this, and it will be going from north to south. You can try the same trick on the second diagram. The positive is still on this side, so we have to begin with the 4 fingers following this blue wire. But this wire passes underneath the hollow tube, so you have to reverse your hand so that your fingers seem to be going under that tube. Grasp around the tube, point with your thumb on the right side, so the North Pole is now on the right and the South Pole is now on the left. You can try the 2 other diagrams. So note that the magnetic field looks like the one around the bar magnet for a solenoid, and the magnetic field never follows the current. It always goes towards the south magnetic pole. You can use this diagram to practice your second right-hand rule. The direction of the magnetic field is known on this diagram. I've drawn the arrows showing where the south and north magnetic poles are. Now, you have to find the correct direction of the current in this system. So we're going to use these 2 circles to mark positive or negative, but you guys have to find on which side they are. So try using your right-hand rule, the second right-hand rule, sorry, to discover where the positive and negative ends are. And using solenoids, it's possible to form what's called electromagnets. An electromagnet is a solenoid where we add a ferromagnetic core. Remember, ferromagnetic substances are usually iron, nickel, or cobalt. It becomes a magnet only if the current is passing through the system. In other words, they're temporary magnets. For example, we could take a simple set of AA batteries or 9-volt batteries, then loop a wire around an iron nail. So the iron nail is your ferromagnetic core. As the switch is pressed, current will flow through that wire. It will create a magnetic field looking like the one around a bar magnet, with a north and a south magnetic pole, and the iron core will become magnetized, which will increase the strength of the magnetic field and make your system a magnet. And as soon as you reopen the switch, the current is shut off and the magnetic field disappears. So the magnet is turned off. This can be used in junkyards, for example, where a lot of metal can be lifted and then dropped later at a different spot by simply turning on or off a switch. And finally, different factors will influence the strength of your electromagnet. The first one is the intensity of the current. If you wish to increase the strength of an electromagnet, you can always increase the strength of your current. The second factor is the number of turns on your solenoid. It will increase the strength of your electromagnet the more you add loops, because every loop you add is more magnetic field added to the total. So this will increase the strength of your magnet also. And the third factor is the nature of the core. Now, the first thing to understand is that if you use a non-magnetic core, it will not add anything at all to the strength of your magnetic field. For example, using plastic, wood, aluminum, or copper, which are all non-magnetic substances, will not add anything. Now, using iron, nickel, or cobalt will increase the strength of your magnet, and iron usually makes for the strongest magnets. But there's a downside in using iron. Iron has high magnetic remnants, meaning that it remembers that it's been magnetized. So even if you turn off the switch, if you have a pure iron core, the electromagnet might remain active for a little bit, even if your current is off.